As this time-lapsed video demonstrates, all of the suspensions will settle if given enough time. Generally, the well-flocculated systems settle faster than the deflocculated systems. As you can already see, suspension 5 has almost finished settling. This is due to the particles aggregating into large, loosely packed flocks, which then fall through the liquid medium very quickly and settle at the bottom of the cylinder. Suspension 3 has also settled well, but the colour and opacity of the medium indicate that the finer bismuth particles are still suspended. This is to be expected, as larger particles in a suspension will always settle faster than smaller ones, due to gravity. This effect is even more obvious in suspension 4, where you can clearly see that the larger particles have already settled, leaving the smaller ones to move slowly down the cylinder. As these smaller particles settle, they will fit tightly into the gaps between the larger particles, expelling any trapped water and creating a very tightly packed sediment. Suspensions 6 and 7 have settled much more slowly than 3 through 5. This is due to the increasing potassium phosphate concentrations causing the systems to become more and more deflocculated. Suspensions 1 and 2 are also very deflocculated. In these suspensions, the low potassium phosphate concentrations cause the particles to remain dispersed, settling very slowly indeed. After 24 hours, it is clear that suspensions 3 through 7 are fully settled. In contrast, suspensions 1 and 2 are still dispersed, with barely any sediment having formed at all. At this stage, measuring the volume of the sediment will allow us to calculate the degree of flocculation for each system. As expected, suspensions 1 and 2 both have very small volumes of sediment. Suspension 3 has more sediment than we would normally expect, but, as we will see shortly, this sediment is densely packed and is susceptible to caking. Suspension 4 also has a densely packed sediment. The sediment in suspension 5 is loosely packed and takes up a large volume. The water trapped within this sediment will allow for easy redispersal of the suspension. Suspension 6 is less well flocculated than suspension 5. The sediment has a lower volume and is more densely packed. Similarly, suspension 7 has a lower sediment volume than suspension 6. Interestingly, in this system, the low zeta potential and high potassium phosphate concentrations have caused some of the phosphate to settle out on top of the bismuth. Due to the slightly acidic pH of the suspension, the potassium has also interacted with our dye, causing it to appear blue. After 7 days, suspensions 1 and 2 have still barely begun to settle. A well deflocculated suspension can take months to settle fully. The week, however, has given plenty of time for the sediment in the remaining suspension to exhibit caking where applicable. This can be demonstrated by attempting to redisperse the sediments. In order to test redispersion, each suspension will be inverted a total of 20 times, or until the sediment is fully dispersed. As you can see with suspension 3, although some of the bismuth does redisperse, the majority of the sediment remains at the bottom of the cylinder, even after 20 inversions. Suspension 4 shows a similar result. Because of their slow settling times and small particle sizes, these sediments are very densely packed. Over time, the pressure exerted by the sediment fuses the particles into a cake, which is then impossible to redisperse. In suspension 5, the particles settled out quickly in large, loose flocks. These flocks trap liquid between them, preventing caking and allowing the sediment to be easily redispersed on inversion. Suspensions 6 and 7 return to the trend shown in 3 and 4. The densely packed sediment has caked, and redispersion is impossible.